So second phase is nothing but it is a planetary motion. So it consists of Kepler's laws, and besides that Kepler's laws, again you have to take that orbital velocity and the geostationary satellite and escape velocity, and again the gravitational potential difference, gravitational potential energy, all these are coming under this second phase. So in this second phase is completely a planetary motion. So first of all we have to start that second phase from Kepler's laws. So in this Kepler's laws, the first one is the first law that you call it is the law of orbits. That is the first law is law of orbits. In this case, each and every planet, so that is each and every planet revolves around the sun in an elliptical orbit, and the sun is at one of its foci. So each and every planet revolves in an elliptical orbit around the sun, and the sun is at one of its foci. So like this it is the elliptical orbit. But it doesn't mean all these planets are rotating only in the elliptical orbits. Suppose for example when you are coming to this, ours is the third planet. So first before that is Mercury is there, and again the Venus, and they are almost rotating in circular paths, but may not be it is the exactly circular path, but they are almost rotating in that circular path. And when you are coming to our Earth and again thereafter Mars, so these planets are rotating in that elliptical paths. And similarly when you are going to that last planets, that is the Neptune and the Pluto, they are rotating in elongated elliptical paths. So elongated elliptical paths, because of that reason for the Pluto to take complete revolution around that sun, it takes 247 years. It takes 247 years. Now here our is the 1 year equivalent to 365 days, and that is the last planet, that is Pluto, that takes 247 years. Now here law of time, that is orbits. Each and every planet rotates in an elliptical path, and the sun is at one of its foci. That is the first one is cleared, and we are coming to the second one. In this second one, the line joining sun and planet, sweeps equal areas. So it sweeps equal areas in equal intervals of time. Sweeps equal areas in equal intervals of time means that is the first one is here like this. We are taking two positions, two intervals we have taken. In this 30 days is there, and again here also we are taking that 30 days is here. 30 days is here, and this is the area covered. So here just we have to recorrect that figure. So in this case the line joining the sun and the planet means it should be taken like this, because that distance is to be taken from the sun. So sun is to be taken here, and again in this case it will be, and it should be like this. So here this is the area to be taken like this, and here it is 30 days, and thereafter it is also 30 days is here, 30 days. So and the area covered, and here the area covered, and both are same in that given interval of time. The line joining the sun and planet sweeps equal areas. Sweeps equal areas in equal intervals of time. Actually that Kepler observed, first of all he observed when that is a planet, when it is moving very slowly, when it is moving far away from that sun, it moves very slowly. And similarly when it is coming nearer to the sun, it moves fast. And after that, by taking that astronomical distances, and he could come to this conclusion, that is a line joining sun and planet sweeps equal areas in equal interval of time. That is, areal velocity is constant. So that's why this law is also known as the law of areas. And here you can have some formula. Now we are taking, it is areal velocity means that can be taken as areal velocity. Areal velocity is equal to area by time. Area by time is taken. And here when you are taking a small angular displacement d theta, and for that small angular displacement d theta, and this is dr can be taken like this, and this is r will be here. Next, area by time means, so you have to take that area of this triangle, and for that it is area of triangle is of BH. So of BH means B is nothing but this distance. So that's why that distance we can consider general distance is a small r only. So small r can be taken. and of B h. H is nothing but the dr is taken. So that dr is also can be replaced by that dr is equal d theta is equal to arc by radius. So that's why dr by r, dr is equal to r d theta. So that's why r d theta is here, r d theta. All this is the area, and as usual by time will be here dt, and again here also dt is here, area by time. Now it becomes a 1 by 2 r square omega is a constant value. 1 by 2 r square is here, and d theta by dt is nothing but omega. So that's why it is a 1 by 2 r square omega, that is aerial velocity is constant. Now it is a second law is completed. The line joining the sun and a planet sweeps equal areas in equal interval of time. Its meaning is that is aerial velocity of a planet is constant. We are taking this area by time, ultimately we got this 1 by 2 r square omega. Now second law is completed. We are coming to the third one. In this third one we are taking that is the law of time periods. Law of time periods means in this case we are taking the square of a time period of revolution. The square of a time period of revolution is directly proportional to the cube of semi-major axis, or it is directly proportional to the cube of average distance between sun and planet. Why it is to be taken as the average distance? Because here in this elliptical path, it is an elliptical path only, it is not at all maintaining the same distance everywhere. So it is not a perfect circle. So that's why it should be, you have to take it is average distance only. So now it is a square of a time period of revolution is directly proportional to the cube of average distance between the sun and planet. Between sun and planet. And for this, how could you get this? And for that we are taking when a planet is rotating around the sun at any instant, CPF should be equal to CFF, that is a centripetal force is equal to centrifugal force. And CPFF is provided by this, that is a gravitational force of attraction between a sun and a planet that supplies a necessary centripetal force. So because of that reason it is a capital G, and again the capital M and small m by r square is here, that is centripetal force. And centrifugal force means it can be taken, that is m r omega square is here. So m r omega square, and next step that becomes it is gm, and here it is r cube is there, m already cancelled, so it is r cube is here, and omega means it is a 2 pi by capital T whole square. So it is a 2 pi by capital T whole square. Next after that it is gm by 4 pi square. Gm by 4 pi square is equal to, that becomes r cube by, so now it is r cube by t square, r cube by t square. As you are already, this value is constant because the capital G is constant everywhere, and mass of that particular planet is also, so mass of that planet is also, planet not the planet, it is the sun, so it is also constant. So that's why it is a t square proportional to r cube, t square proportional to r cube is here. Now these are the three laws that are Kepler's three laws. The first one is a law of orbits, and the second one is a law of areas, and the third one is a law of time periods. So here we are having the two formulae, that is aerial velocity is a constant, for that 1 by 2 r square omega is a constant, and the second one is a t square proportional to r cube. So that's why you can apply that formula t1 square by t2 square is equal to r1 cube by r2 cube like that. So that's why these three laws are completed. Now after that, so that is in case of this orbital velocity. Orbital velocity means the velocity of a satellite in any particular orbit is called orbital velocity, and actually the definition can be taken as it is the velocity which is imparted to a satellite. It is the velocity which is imparted to a satellite so that it can rotate around the earth. So that's why that velocity is known to be that is the orbital velocity. And for that orbital velocity we are taking, this is the earth we are considering it is a perfect sphere, and r is here and m is here, and this a satellite or somebody is rotating around this earth in orbit like this. In orbit, in this case when it is rotating, definitely it experiences centrifugal force. So here we are deriving the formula for the orbital velocity. Once again I tell you the definition of that orbital velocity. It is the velocity to be imparted to a satellite so that it can rotate around the earth, so in a fixed orbit. So now here when it is rotating, it experiences centrifugal force and gravitational force of attraction between the earth and again this satellite that supplies a necessary centripetal force. So for that reason we are taking CPF is equal to CFF, that can be taken, and CPF is equal to what we are taking, it is a capital G and here capital M and small m, by here we are considering this is a H. So now here this satellite is rotating at a height h. So GMM by r plus h whole square is here, and CFF means that can be taken as the mv0 square by r plus h is there. mv0 square by r plus h. So GMM by r plus h, because all these distances are to be measured from center of earth only. From center of earth only. So that's why GMM by r plus h whole square and mv0 square by r plus h, and for that v0 is equal to square root of gm by r plus h is here. v0 is equal to square root of gm by r plus h is there, and thereafter now this is the formula, v0 is equal to square root of gm by r plus h. Suppose if h is neglected, if h is less value when compared to that of the r, in that case v0 is equal to square root of, if h less than capital R, in that case v0 is equal to square root of gm by r, and that also can be taken as the square root of gr. Why? Because here already we know g is equal to gm by r square is there. So that's why gm by r can be replaced by root gr, and this is the formula for a satellite which is rotating, which is revolving around the earth very close to the surface of earth. In that case v0 is equal to square root of gm by r is there, and its value is the 9.8 and again that 6400 kilometers. So it is converted into meters like this, and ultimately you are getting that 7.92 kilometers per second. So it is 7.92 kilometers per second. So it is orbital velocity, and this 7.92 kilometers per second, here it is imaginary only value only. All our satellites have to are rotating less than this value. Why? Because here 7.92 is the velocity of a satellite where h is neglected. When h is neglected, so when h is neglected, then only you are getting this value. Suppose if h is considered, actually practically h cannot be neglected at all, because the satellite is to be taken to greater height only, then only it is to rotate around the earth. So that's why h cannot be neglected practically. If h is not neglected, then automatically this value will be more, this value becomes less than that of 7.92 kilometers per second. So this is orbital velocity of a satellite, closer to the surface of earth, this one, and at a height h is this one, and all these distances you have to understand, these are to be measured from center of earth only. So that is orbital velocity is over, and thereafter we are coming to this geostationary satellite. So geostationary satellite.